This is the introduction to Kafka Connect. Imagine you have a powerful data pipeline with Kafka at its core, but now you need to bring in data from various sources, maybe a database, a cloud service, or even a simple file. And on the other end, you want to send that data somewhere, perhaps another database, a search engine, or a data warehouse. This is where Kafka Connect comes in. It's essentially a tool designed to integrate Kafka with external systems without requiring you to write custom code. There are two main types of connector: source connectors, which pull data into Kafka from an external system; sink connectors, which push data out of Kafka to an external system. Kafka Connect can run in two different modes: standalone mode, which is great for simple local tasks or development environments; distributed mode, which is what you would use in production, allowing you to scale and manage multiple connectors. You might be wondering, why should we use Kafka Connect instead of writing our own data integration logic? There are a few key reasons that make Kafka Connect a solid choice. First, scalability. As your data grows, Kafka Connect makes it easy to scale by simply adding more worker nodes in the distributed setup. No need to manually handle load balancing. It takes care of that for you. Next, fault tolerance. If something goes wrong, say a worker node crashes, Kafka Connect ensures the data pipeline keeps running. It automatically redistributes tasks and resumes processing without losing data. Another big advantage is prebuilt connectors. There are already a huge ecosystem of ready-to-use connectors for databases, cloud services, and more. This means you don't have to write custom integration code, you just configure and deploy. And the final point, configuration-based setup. Instead of coding complex data pipelines, you define everything in a simple configuration file. This makes it easy to manage and update connectors as your system evolves. When we talk about integrating external data into Kafka, we rely on something called source connectors. These are essentially components that allow us to bring in data from various systems, seamlessly fitting it into our Kafka pipelines. For instance, imagine you need to pull data from a relational database, perhaps a Postgres or MySQL instance. In this case, we use the JDBC source connector. This connector continuously reads from the database, capturing new records as they appear, pushing them into Kafka topics for real-time processing. Let's say instead of a database, we are dealing with cloud storage. Organizations often store vast amounts of structured and unstructured data in services like S3. To tap into that and bring it into Kafka, we use the S3 source connectors. This allows us to ingest files from S3 buckets and stream their contents into Kafka topics. Another common scenario is IoT data. Devices, sensors, and various smart technologies generate data in real time, often communicating through MQTT brokers. To capture that data efficiently, funnel it into Kafka, we use the MQTT source connector. This enables us to stream IoT messages directly into Kafka, where they can be processed, analyzed, or routed further. Just as we use source connectors to bring data into Kafka, we rely on sink connectors to send data out of Kafka to external systems. These connectors take messages from Kafka topics and deliver them to various destinations. For example, let's say we need to store Kafka messages in a relational database. The JDBC sink connector makes this possible by writing data directly into tables in databases like Postgres, MySQL, or Oracle. This is particularly useful when we need to persist process events for reporting, analytics, or integration with existing applications. In scenarios where we need real-time search and analytics, we turn to the Elasticsearch sink connector. This connector allows us to stream Kafka data into Elasticsearch, making it instantly searchable. Another common requirement is long-term storage for large volumes of Kafka data. This is where the HDFS sink connector comes in. It enables Kafka messages to be written into Hadoop distributed file system, allowing for scalable storage and big data processing. This is particularly useful for organizations leveraging Hadoop-based data lake for historical analysis and machine learning. Now let's look at Kafka Connect architecture. At its core, Kafka Connect is built around four main components: workers, connectors, tasks, converters. Think of workers as the engines that run Kafka Connect, whether in standalone or distributed mode. These are the processes responsible for executing your connectors and managing tasks. In a distributed setup, multiple workers work together, sharing the load and ensuring high availability. Connector defines where the data is coming from or going to. For example, a JDBC source connector could pull data from a database into Kafka, while an S3 sync connector might write Kafka data into an Amazon S3 bucket. Tasks are the units of work assigned by the connectors. If a source connector needs to read a large database table, it can spin up multiple tasks to read different partitions in parallel, improving performance. The more tasks you have, the better Kafka Connect can distribute the workload across multiple workers. Since different systems have different data formats, Kafka Connect uses converters to translate messages into a format Kafka can handle. The most common ones are JSON, Avro, and protobuf, and they determine how data is serialized and deserialized as it's moved through the pipeline. Let's see Kafka Connect in action with a real-world example. Imagine you run an online store, and every time a customer places an order, the details are stored in a MySQL database. You want to make this database searchable in real time using Elasticsearch. You could write a custom script to move data between MySQL and Elasticsearch, but that would be a pain to maintain, wouldn't scale well. Instead, Kafka Connect makes this easy by automatically moving the data for us. Here's how it works. We have two workers nodes running Kafka Connect. One of them is responsible for pulling orders from MySQL and publishing them into Kafka topic. The other worker picks up the messages from Kafka and sends them to Elasticsearch. This setup ensures even if one worker fails, the other can keep things running smoothly. The actual work is done by connectors. They are like smart adapters that handle the details of connecting to external systems. In our case, we use a JDBC source connector data from MySQL and send it to Kafka. Then an Elasticsearch sync connector picks up the data from Kafka and writes it into Elasticsearch. Moving large amounts of data with just one process would be slow. That's why each connector can spin up multiple tasks to divide the work. So instead of having one process reading the entire MySQL database, we can run several tasks in parallel, each handling a portion of the data. The same happens on the Elasticsearch side, where multiple tasks write data at the same time, making the whole process much faster. There one last piece to this puzzle: converters. Data from MySQL is stored in a structured format, but Kafka and Elasticsearch expect data in formats like JSON, Avro, or protobuf. That way, converters step in. They make sure the data is properly formatted before it gets stored in Kafka and then transformed again before it reaches Elasticsearch. Kafka Connect can run in two modes depending on our needs: standalone mode and distributed mode. Standalone mode is the simplest way to get started. It runs Kafka Connect as a single process, meaning everything, connectors, tasks, and workers, run on just one machine. This is great for local testing or small, simple jobs where we don't need high availability or fault tolerance. We can start it with a single command, which is the first one on the screen. But for real-world production use, we need distributed mode. Here, multiple worker nodes set the workload, making the system scalable and fault tolerant, ensuring uninterrupted data flow. The second command can be used to start Kafka Connect in distributed mode. Let's compare the differences in configuring the two modes. In standalone mode, everything runs on a single machine, and that means we store offsets locally in a simple file. That's why you see this line: offset storage, file name equal tmb connect.offsets. But in distributed mode, things are different. Since multiple workers are involved, they need to coordinate. Instead of a local file, offsets are stored in a Kafka Connect topic, connect offsets. And in addition to that, we have two more topics: connect configs, which stores connector configurations; connect status, which tracks the state of connectors and tasks across the cluster. Another key difference, group ID. In distributed mode, workers need to work together as a group, so we specify group.id equal connect cluster. But in standalone mode, there's no need for a group, there's only one worker. So standalone mode is simple, local storage, no coordination. Distributed mode is built for scale. It relies on Kafka topics to manage state across multiple workers. Let's look at how we configure a connector. Kafka Connect uses JSON-based configuration files. The structure is generally the same, but the exact setting depends on the type of connector you are using. Here an example using a JDBC source connector. This one pulls data from a relational database and sends it into Kafka. We give it a name JDBC source. We specify the connector class. This tells Kafka Connect which connector to use. In this case, it's JDBC source connector class. We define how many tasks it can run in parallel. Task max equal to. The database connection URL tells it where to pull data from. And finally, it adds a topic prefix to control where the data lands in Kafka. But what if you are using a different connector? Where do you find the right settings? Each connector has its own required and optional configuration properties. The best way to find them is check the connector documentation. If you are using a Confluent connector, their website has detailed docs. Look at example configurations. Many connectors come with sample config files to get you started. Use the REST API. If Kafka Connect is running, you can hit the endpoint connector -plugins to list available connectors and see their config options. We talk about how to run Kafka Connect and how to configure connectors, but how do we actually manage them once they are up and running? That's where the Kafka Connect REST API comes in. Kafka Connect provides a simple API that lets us control connectors remotely. No need to dig through config files or restart services manually. Here are a few key things we can do with it. The first command to see what connectors are currently running. The second command to create a new connector. The third command to check a connector is running or not. This list is just the start. The REST API lets us do a lot more, like updating connectors, pausing them, or even deleting them. If you want to explore all the available endpoints, you can check out the Kafka Connect REST API docs. Once Kafka Connect is up and running, how do we make sure it's actually working as expected? There are two key ways to monitor it. First, logs. If something isn't working, maybe a connector is stuck or a task is failing, the logs will tell us. We can watch them in real time with the tail command. Second, Kafka internal topics. Kafka Connect actually stores its state inside Kafka itself using three special topics. One holds connector configurations, another keeps track of offsets so source connector know where they left off, and the last one records connector and task statuses. If something seems off, checking this topic can give us clues about what's happening behind the scenes. Kafka Connect is all about integration. It acts as the bridge between Kafka and external systems. We have seen that there are two types of connectors: source connector, which brings data into Kafka, and sink connectors, which send data out to other systems. It's built for scalability and fault tolerance, making it reliable for production use. And despite its power, the configuration is actually pretty simple. On top of that, the REST API makes it easy to manage connectors. With these tools, we can move data efficiently, scale as needed, and keep everything running smoothly.